All right, welcome back to the drive-thru, everyone. Sponsored by the deli. Hungry? Stop by the deli. Make yourself a bologna and cheese sandwich and a lettuce wrap, maybe. Okay, so you can see here we've got 10-1 number 96, using vectors, prove that the diagonals of a parallelogram bisect each other. So here we've got vector u and vector v, and remember that they don't have any location. They can be anywhere we want. So there we also have vector v and vector u. Now, one thing that's nice about vectors is that we can add them to get a resultant vector. So this red vector right there, we can just refer to as u plus v. And if you've been kind of staying with us lately, then that should make sense. This one's not as intuitive. Notice that the arrow is going this way. Okay, now let me think that through. So that vector there, if I did, let's see, this would be minus v, right? And that would give us that vector. So this right here is u minus v. Okay, good. So I can call this green vector here u minus v. I'm going to erase this because it's going to get dirty enough, if you will. Okay. Okay, now I'm going to want to name this. So let's call this little vector right here, this blue one, let's call that S. That's going to end up being a portion or a half of our diagonal, but we have to prove that. Okay, that's going to be what we're proving. And then we can call this half of the red diagonal. We'll call that R. Okay, now we're going to refer to that picture for the rest of this proof. This is pretty good stuff. So we know that R is some constant, okay, some scalar, times the red diagonal. It's some portion of the red diagonal. It's some portion of u plus v. We know that S is some portion of the green diagonal. Not necessarily the same portion. It's not necessarily A. Okay? It's some portion B of u minus v. Okay? Now, here's the trick. We could represent v, vector v, all these are vectors, 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 vectors. Okay, we could represent v as R minus S. Do you see that on our picture? We travel in the direction of R, and then we travel backwards in the direction of S, and that leaves us to where V ended up. So now let's do some substitution. Okay? So V is equal to R. Okay, well, R is A times U minus V. Okay? Minus B, sorry, there should be a plus V here, times U minus V. Okay, we're going to distribute. Okay, that's a scalar times a vector, so that's still a vector, minus all right, now the distributive property holds true for vectors, so we can rewrite this, okay, as A minus B scalars times vector u, okay? And then this should be a plus here. Do you see how that distributed to make that a plus? Okay, thank you. And then this one will be a plus b, scalars, times vector v. Now, I was stuck when I saw this proof, and I was like, I don't get it. And then you got to remember, this is vector v. Vector v equals some numbers times vector u. Well, vector u is something, so that means that a minus b must equal 0, because there is no vector u in vector v. Okay, and furthermore, since we've kind of eliminated this, vector v equals a plus b times v. Well, a plus b must equal 1. Okay, so that's a system of equations. You get a equals b, so then b plus b equals 1, 2b equals 1, b equals 1/2. Therefore, a and b equal 1/2. If you remember where we started, that means that r is 1/2 of u plus v, which is our diagonal, and s is 1/2 of, let's see, u minus v, which is our other diagonal, and we have successfully proved it in 6 minutes and 52 seconds. Boom!